Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We have been going through a set of lectures in the chapter on optics, and in today's talk we will be having, in continuation with what we have been seeing in the previous lectures, there is a lecture number 13. It is on interference. The contents of this lecture are as follows: change of phase due to reflection, colors of thin films, conditions for constructive and destructive interferences, interference in thin films, and lastly conditions for bright and dark fringes. We have been discussing about coherent sources in the previous lecture. Unless we have coherent sources, we will not be getting the interference pattern. What do you mean by coherent sources? I told you that there should be 2 light sources, and the light coming from these 2 sources should be interfering, and the resultant is the one that we are trying to observe. The sources should be having the same wavelength, they should be emitting light of the same wavelength, and the phase difference of the 2 light waves should be constant. So, the conditions are 0 phase difference, the sources of light which emit light waves continuously are of the same wavelength, time period, frequency and amplitude, and a 0 phase difference or constant phase difference. That is the case, they are called the coherent sources. The other important factor is you should know what is meant by path difference and the connection between path difference and phase difference. Now, what is meant by path difference? I told you in the last lecture also, the extra path that is travelled by one of the light rays compared to the other light ray, the additional path or extra path is called the path difference. Now, look at this diagram. You have got S1, that is the source 1, S2 is the source 2, and light travels from source 1, it travels through a distance R1, whereas the light from source S2 travels through a distance R2 as indicated in the diagram. So, obviously, the distance R1 is greater than R2. So, the difference in distance or the extra distance travelled by one of the light beams, because R1 is greater than R2, this delta will be equal to R2 minus 1 R1, you should take only the magnitude. So, the extra distance travelled by one of the light beams compared to the other light beam is called the path difference. And again this path difference can be converted into phase difference using the following expression, namely delta phi will be equal to 2 pi times delta by lambda. Phi is the phase difference or delta phi is the phase difference. You have got 2 pi into delta is the path difference divided by lambda, and this obviously will show a phase difference of 2 pi corresponds to a path difference of lambda. A phase difference of 2 pi corresponds to a path difference of lambda, or vice versa. A path difference of lambda will correspond to a phase difference of 2 pi. So, the path difference is a very important concept. Now, the path difference should be lambda or 2 lambda, that is the condition for what is called constructive interference. As we proceed, we will see the importance of path difference or the phase difference. And yet another important point is there is a phase change when light is incident from one medium to another medium. In under what condition there is a phase change? When light travels from air to glass or air to water. What do you mean by this? Air has got a refractive index 1, whereas water is having a refractive index 1.33, or you can have glass is 1.5. Therefore, air is a rarer medium, as all of you know by now, glass is a denser medium, and so when light is incident from a rarer medium on the surface of a denser medium, as shown in the diagram here, right. You see air here, that is having a refractive index N 1.0, whereas N 2 is glass. N 2 may be glass or water, which has a refractive index 1.5 or 1.33. Okay. So, when light is incident from a rarer medium to a denser medium, there will be a phase change of 180 degrees. This can be experimentally observed in the case of a soap bubble, okay, a soap bubble or whatever be the thing, a soap bubble made up of water and all, you can see the phase difference, the light being reflected, and you can understand, or electromagnetic theory shows that there will be a phase difference when light from a rarer medium is incident on the surface of a denser medium, as shown in the figure 1. Whereas, in the figure 2, it is the other way around. Light from a denser medium is incident on the surface of a rarer medium. You have got a rarer medium here. There will be no phase change. So, in the second case, there will be no phase change. So, when light is going from glass and falls at the top, at the bottom of the glass surface, which is the interface between glass and air, right. This is the bottom. Okay. When the light is incident on this surface, which is separating the denser and rarer, there will be no phase change. On the other hand, you have got rarer medium here, denser medium here. When light is incident on this surface, on the surface of a denser medium, from rarer to denser when light goes, when it is incident on the denser medium, then there will be a 180 degree phase change. 180 degree phase change will correspond to 180 degree means pi, a phase difference of pi will be there. So, path difference of lambda corresponds to 2 pi, or a phase difference of 2 pi corresponds to lambda. So, if there is a phase difference of 180 degrees, that means it is pi. So, a phase difference of pi will lead to a path difference of lambda by 2. So, this kind of reflection, that is when a light wave, when it is incident from a rarer medium on the surface of a denser medium, it is reflected back, then there will be a phase difference of 180 degrees or a phase difference of pi, which correspond to a path difference of how much, lambda by 2. Okay. That is a very important point. This should be remembered, because this we will be making use of in the time to come, when you are discussing about air wedge or colors of thin films or neutron strings. This phase difference, this particular idea will be made use of. That is, you should remember, whenever light is incident from a rarer medium to a denser medium, at the surface it is getting reflected. When it is getting reflected, it undergo a phase difference of 180 degrees or pi, that corresponds to a path difference of lambda by 2, that should be noted down. Then this corresponding mechanical analogy is given on the right side, a string analogy, in which case you have got a crust here, then when it is getting reflected, you have a trough, there is a 180 degree phase difference is there. On the other hand, in this second case, you have a hump. In the reflected case also, there is a hump or a crust. Okay. that there is no phase change. This is a mechanical analogy, but anyway the point is, as I told you, the optical concept that I told should be borne in mind, because that will be made use of in the lectures to come. When two light waves from different coherent sources meet together, then the distribution of energy due to one wave is disturbed with the other, they interfere with each other. This modification in the distribution of light, or when the two waves interfere, the resultant that you get is important. The superposition of two light waves, that leads to what is called the interference of light, and as I told you, repeat it again, the conditions for interference are the two light sources should have the same wavelength, phase coherence should be there, they should be very close to each other. In the last lecture I told you have the two slits S1 and S2 in the Young's double slit experiment. If they are far apart, then there will be the two will be as two independent sources, right. There will be no interference, will be the waves will not be interfering with each other. So, the S1 and S2 should be very close to each other, that is another important point. Then you go to what is called the constructive interference. In the last lectures also we saw that when a crust meets a crust or a trough meets a trough, that will be constructive interference. So, what I am trying to repeat it again, crust meeting a crust or a trough meeting a trough from the second wave, you will have what is called an constructive interference. Now, I am going to give a mathematical thing, namely for constructive interference the path difference should be integral multiple of lambda, right. This is a very important point to be noted. For constructive interference, that is when two light waves are interfering with each other, if you want to have constructive interference, what is the constructive interference? The resultant displacement should be very large, or the intensity should be very high, leading to a bright band. So, the condition for obtaining a bright band or a bright fringe is the path difference between the two light waves should be integral multiple of lambda. So, m will take values 0, 1, 2, 3 etcetera, or the path difference should be 0 or lambda. You can have m 1, 2, 3 and so on. So, the path difference should be 0 or lambda or 2 lambda or 3 lambda. Okay. So, the path difference should be integral multiple of lambda if constructive interference were to take place. We will see what is the condition that should be obeyed to be satisfied for destructive interference to take place. You can infer now, when a crust is coming, another crust is coming, crust and trough should meet each other. So, the distance that separates the crust and trough is lambda by 2. So, you can infer what should be the condition for destructive interference. So, a destructive interference occurs when a crust is meeting a trough. Okay. That is the thing that will lead to a destructive interference. So, if the path difference between the two light waves is m plus half into lambda, then the destructive interference between them will be destructive. So, the condition for destructive interference is the path difference should be m plus half into lambda. If m is 0, as I told you, lambda by 2. Lambda by 2 means what? Half the wave. So, that means when a crust is coming from the first wave, trough will be coming from the second wave. So, crust and trough will meet. What is crust? The displacement on the upper side, trough is the displacement in the lower side, the water particle going down, here the water particle is going up. So, by the same amount, therefore, A minus A, as I told you, will be equal to 0. So, when a crust and trough meet each other, so or in other words, if the path difference between the two is lambda by 2 or 3 lambda by 2 or 5 lambda by 2, under these conditions the crust and trough will meet, leading to nil displacement or nil intensity or a dark fringe or a dark band, that is called a condition for destructive interference. Okay. So, the effects that you get, what are the effects? Either you have a bright band or a dark band or a dark fringe in the screen because of the interference that is occurring between the light waves coming from the two sources S1 and S2. These effects will depend upon the path differences between the two light waves. So, the path difference is m plus 1 into lambda by 2, that is the condition for destructive interference. As I told you just now, the path difference should be lambda by 2 or 3 lambda by 2 or 5 lambda by 2, that is the condition for the destructive interference. The condition for constructive one is lambda to lambda, integral multiple lambda. Okay. Let us now pass on to what we call as colors of thin films. Now, what do you mean by colors of thin films? When we generally tell colors of thin films, one may not be understanding what we mean by a thin film, what is the meaning of colors. When you walk along the road on a sunny day, if there is water on the road and if oil would have been spilled on the petroleum would have been spilled on the water surface, you get a fine film. You would have seen when you walk along the road, water on the surface of the road, and along that, over that there will be a film or a few drops of oil would have spilled over or petrol would have been spilled over. Then when you see in not in the night, the daytime sunlight is falling on the film. What do you mean by film? That is a layer that you have, layer of kerosene or of layer of oil or layer of petrol on water. On water will be having a layer, and this layer thickness will be very small, from a few nanometers to 1 micron meter, 1 micron, right. So, I mean very thin film that you have on the surface of water, that is what you mean by thin film, right. What is thin film? This is a thick material, this is a bulk material. Thin film is one whose thickness is very small, a few nanometers to, nano means 10 to the power of minus 10 of a meter. So, from a few nanometers to microns, 1 micron. So, that is a thin film. What is that thin film? That thin film may be petrol or kerosene or some oil that has fallen inadvertently on a pool of water. Then you, when you see that water, when you see clean water, nothing is in, but when petrol or kerosene has been spilled over water, then you get see the colors, right. Or you see similar colors on a soap bubble. When light is incident on a soap bubble, you get see the colors on a soap bubble. You know, go to washing machine or you have soap and something, you wash your clothes and you get bubbles. When light is incident on the bubble, you see the color, the coloration, right. This is what you mean by you know, the colors which are produced by thin films. Now, these are, you see beautiful colors, right. You see colors on soap bubbles, somebody is having number of bubbles, right. So, you produce bubbles and you see colors. Now, these colors that you get are due to the fact that light is incident on this bubble. What is this bubble? Bubble is not a big water drop, it is inside, it is empty, and you have only a film which forms a bubble, right. You have inside there will be nothing, it will be air will be there inside, and outside will be having air, and you have got a bubble, and this bubble will lead to some coloration. When light is incident, you will see, you could have seen bubbles and the colors. And the second thing is this is what I told you just now. When you are walking on the road, you see a pattern of colored light formed by interference between white light being reflected from the surface of a thin film of diesel, say diesel or petrol, which is which has been deposited or which has fallen on the surface of water, the diesel water interface. This is a diesel, this is water here, you got some diesel, and you see the colors, right. Many people would not have paid much attention to this phenomenon. You know, when you walk on the road, you see this kind of thing, that is colors, right. You know, water and then some oil would have spilled over water surface, and you see the colors, and you may not be interested in knowing why the colors are occurring, right. So, it is the interference phenomenon that leads to the colors. That is what you mean by colors of thin films. Let me go back and show the beautiful soap bubbles and so on. So, the colors of thin films, a thin film is a layer of material with thickness in the nanometer to micron range. As light strikes the surface of a film, it is either transmitted or reflected. Whenever light is incident on a surface, it will be partly transmitted, partly absorbed and partly be reflected, right, at the upper surface. Light that is transmitted reaches the bottom of the surface. You have got a surface like this, it may be a glass piece. Light is incident here, partly it is reflected, and a part of the light will go and it will be reflected by the bottom surface, right. The point is, light will be partially reflected by the top surface. That light which is transmitted inside the glass piece, it will be again reflected, and there may be transmission also. Let us not now worry about the transmission. Light is incident, it is reflected, and a portion of the light would have gone inside and getting reflected from the bottom, right. Then that will also come. So, these two light rays, what are the two light rays? One reflected by the top surface, the other reflected by the bottom surface. These two light rays may interfere, will interfere. Now, depending upon the thickness of the film, depending upon the nature of the material, the refractive index, it may be oil or it may be kerosene or whatever be the thing, right. So, depending upon the film thicknesses, the film thickness is the refractive index and the angle of incidence and so on. Depending on these factors, the light ray reflected by the top surface, light ray which is coming from the bottom surface, they will interfere, leading to either constructive or destructive interferences. The interference effects are commonly observed in thin films, such as thin layers of oil on water. So, oil on water, petroleum on water, or any kerosene or whatever be the thing on oil. So, that is the film. We are talking about a thin film, and that leads to coloration. I showed you soap bubble again, very beautiful soap bubble, and that also will show different colors, right. The bubbles have different dimensions. On the surface you got film, and the light is incident on the film. Again, light is incident here on the top and the bottom also. Light is incident reflected by the top, and of course, the bottom also will be reflecting light. It is a very thin film, right. Thin film of the order of micron or less than micron, a few nanometers, right. So, this thin film, because light is reflected on the top surface, you see the bottom is here, right. This is the whole bubble, right. Inside you do not worry about the inside inner region. So, the light reflected by the top, the very thin film, light reflected by the bottom, these two will interfere and will give rise to the colors. The varied colors observed when white light is incident on such films, they result from the interference of waves reflected from the two surfaces of the film. What are the two surfaces? As I told you, the top surface and the bottom surface, but the thickness is not this much. This is for example, I am showing, but actually I showed the film thickness will be very small, because a soap bubble, you just imagine a soap bubble, the top and the bottom, right. The thickness of the bubble is so small, you can, the human eye cannot be used to measure, or the scale cannot be used to measure the thickness of the film. The thickness will be very small, and again the layer that is formed on water, and the thickness of a oil layer or petroleum layer, they will be very, because a few drops are falling on the surface of water, again a film is produced, the film thickness again will be very small. Okay. This is a film, and because of this, because the thickness of the film will be different regions, and because of that you get various colors. So, the colors that you obtain because of thin films, because of that reason, this section is called the colors of thin films, and you want to scientifically explore what do you mean by colors of thin films, and when will you be getting constructive, destructive interference and so on. As I told you just now, I showed this particular thing as an example, light being incident on the top surface, light being incident on the bottom surface, both light rays being reflected, and this is what is being shown here also. You have got air here, and with refractive index N1, what is N2? N2 is the refractive index of this medium. What is this medium? This medium that I am showing here is the bubble, that is the top surface of bubble, this is the bottom surface of the bubble. or the top surface of the petroleum layer, a thin layer which is appearing on the surface of water. You got surface when you walk along the road, you see some pool of water and you have got some oil being spilled or petroleum being spilled on the surface of water, and a thin film is there. The thickness of the film is so much, it is of the order of micron or submicron range, a very thin film, right. But for mathematical convenience, I show this as a thickness of film which can be seeable, but actually it is so small. So, the incident light getting reflected by the top surface, as I told you, then a part of the light will be transmitted, it goes to the bottom surface of the film, is the film, right, and getting reflected from the bottom surface. So, the light is emerging from this point C, and the light AD, the light ray AD and the light ray that is coming along this direction BC, and these two light rays, the reflected light rays coming from the top and the reflected ray coming from the bottom, these two will interfere, and depending upon the conditions which they satisfy, you get the bright or dark fringe. Let me now summarize the points which emanate from this lecture. Point number 1, there will be a phase change of pi when light is reflected by a denser medium. The second point is a phase difference of 2 pi will correspond to a path difference of lambda. Colors of thin films which appear on the surface of oil or water or soap bubble or due to this phenomenon of interference. Light reflected by a thin film, depending upon the light ray falling on the top surface and the bottom surface and other things, there will be bright or dark bands will be occurring, and colors can be explained using the mathematical formulation which we will be seeing later. Here are the questions for today's lecture. 1, when a light wave encounters a denser medium and gets reflected, will it undergo a phase difference? Question number 2, what do you understand from the words colors of thin films? With this we come to the end of lecture number 13. The theoretical expressions which are to be obtained with regard to the colors of thin films we will see in the lectures to come. Thank you.